Hi! As we all know, software is at the foundation of application specification and development. Whether the end application is targeted towards medicine, automotive, machine learning, entertainment, or gaming, most products available today began as software model or prototype that needed to be accelerated and executed on hardware device. Within this scenario, software engineers are required to determine the execution device to get a solution to market and to achieve the highest possible degree of acceleration possible, which is a perfect scenario for our FPGA-based system. Now, what we are going to see in this class is exactly this: how to program an FPGA. Well, more than really how to program an FPGA, we are going to see what is needed from a programming description language point of view. Essentially, programming an FPGA means the ability of describing the desired system behavior and to move this description into an FPGA reconfiguration bitstream file. We know that an FPGA is a kind of an empty page that we can fill with the desired system. This is huge, because the desired system can be a very different concept idea from user to user. Can we use the FPGA to implement a classical von Neumann architecture to prototype a core or a processing element we are interested in designing? Can we design a cryptographic core to cipher a certain kind of information? What about implementing a protein folding algorithm or the Smith-Waterman algorithm to perform local sequence alignment? Well, those are all great examples of systems that can be implemented on an FPGA. Frankly speaking, that's not even completely true, because in some cases they can also be implemented by using multiple FPGAs. Now, this is huge. And this is huge because this means that when interested in using an FPGA, we may be facing also the need to define not only the specific behavior of a single functionality, but also the definition of the entire system in which it will be embedded. And by doing this can imply the design of a proper communication interfaces, deciding how to interact with memory hierarchies, and this is just to cite few of the things to be taken into consideration. Within this context, I think it's quite clear why we need languages that we can use to program an FPGA-based system. And, if I may, I think it should be also quite clear why there is the need to have different programming languages. What is the system you will be interested in creating? What is its complexity? Now, based on this, we have to decide which language is going to be the best for us. Are we looking for a quick and dirty implementation that we can use to prove that our idea is working and we can refine it later as needed? Are we looking for performance, no matter if in terms of area, power, energy, or throughput? If we are considering writing a program for a CPU-based system, I think that we can all agree in saying that one of the most known programming languages is C. C is definitely not one of the newest programming languages, but looking at the ranking for the top 10 languages for the typical IEEE Spectrum reader, we can see that even in 2017, C is placed at the second place. Again, this depends a lot on what you have to do, in the complexity of the system you have to realize, and in what you are interested in getting out of it. But still, even if C is an old language, it is not uncommon at all in using it today. That same thing is happening when coming to the question on how to program an FPGA. Two old hardware description languages to help us in describing the desired system behavior by specifying functionality of logic at a high level are VHDL, which stands for VHSIC Hardware Description Language, where VHSIC itself stands for Very High Speed Integrated Circuits, and Verilog. Once we have our input specification, we need tools to validate it. Validation is a very important phase. Through high-level simulation, we are going to be able to catch specification errors. Furthermore, considering that, as we said, we can have our component to be just a part of a more complex system, or because we may be interested in having a certain performance, we can use the validation phase to verify pin output and connect to other system components, and at a lower level, to verify mapping and check performance. At this point, we have a specification of the system we are willing to implement. We have been able to validate through high-level simulation, but we need something that is going to allow us in generating the necessary configuration bitstream file. This will be done, first of all, through the logic synthesis, which can be seen as the process of compiling an HDL program into a logic gate and flip-flops. The logic synthesis alone may require an entire or even more course to be properly described. Therefore, I don't want to guide you through these steps in details, but I'd like to give you an idea of what is happening behind the scene to better understand the complexity of the processes carried out by the tools you are going to use. What we are now interested in doing is in mapping the logic gates and flip-flops we have onto the elements available in a specific technology because of the FPGA chosen to implement our system. Because of this phase is called technology mapping. The output of the technology mapping phase is a netlist. Within this context, we can see the technology mapping as the process of describing a circuit with a netlist that consists of only gates belonging to a specific technology library. Now, at this point of the process, we move from a pure description of our specification to something which is starting to look like as the underlying hardware that will be used to implement it. We have a netlist defined by elements of a given library, but still we don't know exactly which instance of an element will be really used onto our hardware device. In other words, we may know that a certain part of our input specification will be implemented with a certain number of LUTs, as an example, but we don't know which LUTs are going to be used on our FPGA, and this is something which is not acceptable. To solve this issue, we need to go through a new phase of our process. We need a placement and routing phase. The placement and routing phase assigns logic blocks to function, and by doing this, we are going to know exactly which element on our device will be used to implement which component in our specification. Once that the elements are placed, we need to make wiring connection. Data has to move. We need connection in between elements to allow this. Obviously, things are not easy, and the placement and routing are not two subsequent separated processes, but they are strongly connected. A decision on where to place an element will have a huge impact on the routing and vice versa. Once that everything has been found in implementation, we need to verify a few more things. One for them is the timing. We need to go through a timing analysis to determine delays because of the previously taken decisions, to look at the critical paths and ways to improve them. At the end of this process, if everything is respecting the system requirements, we can generate programming files. This is the phase used to generate the well-known bitstreams to be loaded into the FPGA configuration memory for configuring it.